Thank you for inviting me, and apologies that there are no algorithms in this talk. But I've been enjoying the conference a lot so far, and my impression is that although there are no algorithms, it's not a complete outside talk. So the topic will be evolving networks. And I'm going to report on ongoing joint work with Emmanuel Jacob from ENS in Lyon and Amitai Linker from the University of Chile, who will soon move to France and then on to Cologne. So the topic or the question that I'm interested in is to understand how processes on large complex networks can be affected by the time variability of the network. So what we're going to study is, so this process on the network is the contact process. I'm going to say what this is in a minute, and then we will run it on a random graph, a scale-free network, and then we will put a stationary dynamics on this network and see how this stationary dynamics influences the behavior of the process. So the contact process is one of these epidemic processes, also known as the SIS infection. So it's an epidemic process describing the spread of an infection or of information on a finite graph. So everything will be about finite graphs. So in this case, every vertex of the graph you can think of as an individual, and that can be either healthy or infected. And an infected vertex infects each of its neighbors in the graph at a fixed rate lambda, positive, and every infected vertex recovers with a fixed rate that we set to 1. And importantly, once recovered, a vertex is again susceptible to infection by its neighbors. So the state of a vertex alternates between, on the one hand, being healthy and susceptible, and on the other hand, being infected. So that's why it's also called SIS, for susceptible, infected, susceptible. Right, so this is a finite graph. It's a very easy Markov chain, finite state space, and if you think about it for a second, there is one special state there, one absorbing state, and that's the state that every vertex is healthy. Once every vertex is healthy, the infection has died out. And because you can reach this state from every other state, eventually the infection will die. And the situation that we will be most interested in is that the infection has broken out, so we assume that every vertex is infected, and we ask how long does it take until the infection has died, and we're in the state that everyone is healthy. Okay, so this is the extinction time Tx, and at the extinction time all vertices become healthy and remain so forever. We start with all vertices infected and ask how large is this extinction time. And there are two principal scenarios that can occur, and one I call fast extinction. And fast extinction means that for a sufficiently small but positive infection rate lambda, the expected extinction time is at most polynomial in the number n of vertices in the graph or in the network. So when I say network, I mean a sequence of graphs. Capital N is always the number of vertices, so it's a sequence indexed by this number n of vertices. If there exists a positive small lambda such that the expected extinction time is polynomial in the number of vertices, then I say this fast extinction. And the alternative is slow extinction, and that means that for every infection rate lambda, no matter how small, there's a high probability that the extinction time is at least exponential in the number n of vertices in the network. Okay, and behind this there is a sort of physical scenario. If you think of this system as sort of a particle in an energy landscape, in the fast extinction case, you move very quickly to this lowest energy state where everyone is healthy, whereas in the slow extinction case, there are local minima in this energy landscape, and you get stuck in these local minima, and this is what the physicists call metastability. So if you run the simulation with a large network, and you're in the slow extinction case, you would not guess that you actually end up in the state where everyone is healthy, because you will spend a very, very long time here in the state where you have a varying, but essentially varying around a fixed value number of infected vertices, where you're sort of in a quasi-stationary state there. Okay, and only when a very rare disaster happens, and then everything will collapse and the infection will die out. So that's sort of the two scenarios, and we want to find out which of these two scenarios prevails. This is a very rough question, right? I'm not going to deal with the question what this critical lambda is. I'm only interested in the case whether it's sort of zero, as in this case, or positive, as in the case of fast extinction. Okay, so that's the contact process, and I'm going to study it on graphs that form a scale-free network. So I'm going to explain my graph model. So a feature of many networks is that they're at least approximately scale-free, and for us this means that for very large network size and a large k, the proportion of nodes of degree k decays polynomially. So like k to the minus tau for an important parameter, which is called the power law exponent tau. So this is not an Erdős-Rényi, for example, where you have even super exponential decay for the proportion of nodes of degree k, but you have a much slower decay. So there are vertices with very high degree in the network. So there's huge inhomogeneity in there. This is sort of the defining feature of these graphs. This big difference between vertices of a few vertices with very high degree and the bulk of vertices with order 1 degree. So how can we create such a network, such a sequence of graphs? There are lots of different possibilities, and I'm picking the easiest. And there are two reasons for why I'm picking the easiest. First of all, I want to avoid unnecessary work, as everyone does. But then there's a second better reason, and this is that I will eventually put a stationary evolution on these graphs, and the easier the model, the more natural stationary evolutions can have this as an invariant distribution. So if I have a complicated model, the evolution that I'll put on is necessarily so complicated that you wouldn't consider it natural. So that's a reason to keep it as simple as possible. And the simplest case is the so-called inhomogeneous random graphs. And the idea is that we describe the vertex set of this of the graph of size n just by the numbers from 1 to n, and the meaning is that these are sort of ranks, and vertex number 1 is the most powerful one, 2 is the second most powerful one, and the ones that have an index of order n are the bulk, the least powerful ones. So small indices indicate large strength. And then we connect every pair of vertices independently. And this independence, of course, is what makes the model easy and tractable. And the probability of connecting the ith and the jth index vertex in the network of size n is given by a kernel P, with two arguments on the interval 0, 1, and this kernel P is sort of decreasing in both components, and we put in the indices I and J rescaled to be in the interval 0, 1 in there. So the smaller the index, the larger this value P here, because we assume that P is decreasing in both components. Okay, then we take this value here, we divide it by n. Why do we do this? Well, we want to create a sparse graph, and we have n possibilities, or n-1 possibilities of vertices to connect to, so this is compensated by this 1 over n there. I'm sure I don't want to shut down the computer. What should I do? Cancel. Oh, but I can't do it with this one. Oh, I can't do this one as well. With the mouse? Oh, yes, that looks good. No, I can't. Okay, good. Okay, maybe this was a warning because this number here could be bigger than 1 in this case. To make it a probability, I just cut off at 1. Okay, so I take my vertex sets 1 to n, and I have a probability Pij of connecting the ith and the jth indexed vertex, and I do this independently for every pair I and j, which are distinct. So what kind of Pij do I want to put in? Well, I want to put in the probabilities, more or less, that I get from all the scale-free models that I know. And if you choose your favorite scale-free network model, like you could choose a configuration model or Chung-Lu, Norris-Raitu, there's a whole bunch of them around, and then you discover that they have connection probabilities that are at least asymptotically of the form that this kernel P here is P of xy is some constant multiple of x to some negative power times y to some negative power. So the dominant structure here is that in these models, the probability of connecting the ith most powerful and the jth most powerful vertex is given by the product of a feature of one vertex and the other vertex. So there is this product structure in here that's sort of characteristic. So I'm claiming that if you did what I'm doing here with these inhomogeneous random graphs with the configuration model, we would get the same thing if you choose this factor kernel. There is one random graph model or scale-free graph model that's different on the market, and that's preferential attachment. The preferential attachment kernel, we've heard about this in this conference. So this is a recursively defined graph model, and if you look at the probability of connecting, in this case the power is the h, the ith created and the jth created vertex, you have a connection probability which is of the form given here, so some constant multiple, and then the minimum of x and y to the power minus gamma, and the maximum of x and y to the power gamma minus 1. So this is a considerably different kernel here, and while this is special in the fact that it has this rank 1, this matrix here, Pij's rank 1 there, in this case this is special because when you plug this P in here, the n dependence drops out. And that actually means that it's recursively defined. You can get from this vertex of size n to the vertex of size n plus 1 without changing the edges that are already present. So actually every model that I've seen studied is essentially has connection probabilities of this structure essentially. If you have an interesting model that has a different kernel P, then I would be interested to hear, because our methods are for general kernels P. I only present the results for these two, in my opinion, most important cases. So there is a parameter gamma in the interval 0, 1 in here, and this is the one that that allows us to control this power law exponent tau, and the formula, which is you can easily check, is that tau is 1 plus 1 over gamma. So if because I'm making reference to both tau and gamma all over the talk, so I write for your convenience this formula here. So gamma is the parameter that we put in the model, but the really interesting feature is this tau, this power law exponent that we get. And when gamma varies from 0 to 1, this tau varies from infinity down to 2. So small values of tau means large inhomogeneity. It corresponds to large values of gamma. Okay, so this is the easiest way to define scale-free networks. And for the type of question we look at, the more classical models will behave in the same way. Although, of course, of course, I emphasize this is not the preferential attachment model. That has more little dependencies between the edges that turn out not to be relevant for the kind of question we ask, but we've removed them. So it's a kind of linearized version with all the interesting features, I believe, of the model. Okay, any questions about this static graphs before I make them evolve, before I let them evolve? Okay, good. Right, our question, you remember, we had put a contact process on these graphs and ask whether you have slow or fast extinction. This question has been treated about 10 years ago. There were several papers, and maybe the one that fits our setup best is by Chatterjee and Direct from 2009, and they show that for all values of tau, or if you want gamma, the contact process shows slow extinction. So that's the metastable situation, and that's the situation that's different from when you put this on, say, a regular graph, where, of course, you have fast extinction because there are parameters, positive infection rates, where you can have just polynomial extinction time. But this is not possible here. You have slow extinction, so there is this phenomenon that the infection can survive for a very long time, and I'm going to explain in a minute how this is happening. But this is a starting point, an interesting starting point, because this result, this paper that caused some stir, because there was, it's an older paper, or several older papers in the physics literature, who do a mean field calculation and predict a different behavior. They predict a phase transition between a slow and extinction and a fast extinction phase that happens when tau passes the value 3. So what we have here is a different mean field behavior from the behavior of this static network, and that this is possible this is possible because the contact process, when it spreads the infection, it reuses edges. There are some important edges in the graph that the infection uses several times to pass. The infection is passed along these edges several times, and it makes a difference whether, as in the mean field model, every time you want to use an edge, you resample whether it's in the graph or not, or, as in the static case, you decide once and for all whether it's there or not. And this makes, of course, the question interesting, that when you now let the network evolve and have an edge being present for some time, but then maybe remove it and then recreate it, that you sort of see a behavior that might be in between these two extremes. And that's actually what we will see. So let's say how we let I let the network evolve. So as I say, I want to put a stationary distribution on this. I now have so a dependence on a continuous time parameter t in my graph. So the vertex set is always 1 up to n will still go to infinity. At time 0, I form I independently connect every pair ij with the same probability as before. And now I evolve the network. And there are two natural ways how I can do this, which I call vertex updating and edge updating. So vertex updating means every vertex has a clock, right? So there's a Poisson process associated with every vertex, and this clock strikes after an exponential time with the parameter that I call kappa. And when the clock strikes, say for vertex I, all adjacent edges are removed and new edges are formed starting from this vertex I, and I use the same probabilities Pij to create the edges from I. So this is sort of a baby model of for a graph where the edges represent spatial closeness and where the individuals move somewhere else. So the idea is you are this individual, you move somewhere else, and then you're close to different people, and therefore your entire neighborhood changes. There is, of course, an alternative that if I have time mentioned at the end, that would be edge updating, in which case every edge has a clock, or every potential edge has a clock, and when it rings, I decide whether it's there or not. That would be a much slower dynamics in this case. It's equally valid. I'm going to show you results about this at the end. But the main part, the more interesting thing, is this vertex updating rule. And you notice that at all times t, the law of the graph is the same as at time 0, so it's a stationary dynamics. Okay, so now I'll have my contact process, and independently I have the evolution of the graph, and the question is, do I see fast or slow extinction? And the first result of this talk is from 2015 with Emmanuel Jacob, and we look at this network with a factor kernel, and we notice the following dichotomy. So if tau is less than 4, or equivalent, if you look at this formula, gamma bigger than a third, so if you have a strong inhomogeneity, then you have slow extinction. So no matter how small the infection rate lambda is, the probability that you become extinct in less than exponential time is exponentially small. So in other words, you need an exponential time to, until your infection dies out. Whereas when tau is bigger than 4, you can have fast extinction, so there exists a critical parameter, and when you have an infection rate below that, the expected extinction time is less, it's just polynomial, in fact, it's less than n to the gamma, that's the right exponent, times log n, which is something that occurs from the proof. Okay, so we note two things. Remember, in the static case, when the graph was not evolving, we always had slow extinction, and here the time variability has made fast extinction possible, but only when tau is bigger than 4. And that was very surprising, because I already mentioned the mean field prediction due to Pastor, Sartoris, and Vespignani, and that finds a transition between fast and slow extinction when tau is equal to 3. And tau equal to 3 is what people working on scale-free networks expect as a typical phase transition point, because the topology of the graph changes when tau passes the value 3. So for example, when tau is less than 3, the typical distance of two points on the graph is doubly logarithmic in the size, whereas when tau is bigger than 3, it's logarithmic. If you look at the percolation, the critical percolation parameter, that's 0 when tau is less than 3 and positive when tau is bigger than 3. So phase transitions at tau equals 3 are standard. Phase transition when tau equals 4 is very unusual, and I'm going to explain in the next slide why we have this value 4 instead of 3 here. But it's actually a very a thing that sort of came as a surprise when we did this. So let's do this mean field calculation, or a very easy version of it, to get the behavior in the case when you update your edges very fast, so that whenever the infection wants to travel an edge, it's already updated compared to the time when you last traveled. Okay, so the setup is very easy. You have your set of vertices from 1 to n. Remember, the ones with the small indices are the powerful ones. So you put up a threshold, a of lambda, which goes to 0, so that the vertices from 1 up to a of lambda times n, these are the ones that you want to work with. These are the powerful ones. We call them stars. The other ones we call connectors, that are the sort of the bulk vertices. And we want the infection to survive on the set of stars. Why is this? Because the stars are the vertices with the high degrees, normally in infections you have sort of a critical lambda, which is of the order like 1 over the degree. So if you want to show that the critical lambda is 0, you want to look at the ones with a high degree, because that's where things are happening. So you want to sustain your infection on the set of stars. So what you're doing is you sum over all the stars. Assume that you have a proportion of them infected. You look at whether they infect before they recover another star, and the ones that are infected in this way, the number should again be a proportion of order a of lambda. So that's what this calculation says, and I've already replaced the Riemann sums that occur there naturally by integral. So you go over all the stars, of which you assume that you initially have a proportion infected. Pxy is what remains of the probability that the star x is connected to the star y. So you go over all the stars here you want to infect. This is the probability that there is an edge, and lambda is the probability that before you recover, the infection will pass along that edge, because lambda is the rate at which the infection passes along edges. And that should again be of order a of lambda. So that sort of tells you, if we can set it up like this, then the stars defined with this a of lambda will be able to retain the infection. So we plug in the factor kernel. I'm dropping all the constants. So this is x to the minus y to the minus gamma, x to the minus gamma, y to the minus gamma. We have a super easy integral. Lambda times a of lambda to the 2 minus 2 gamma should be of like a of lambda. And then if you put this to this side, you get this rule, and then you notice, because lambda goes to 0 and a of lambda goes to 0, you want this exponent to be negative, and that happens if gamma is bigger than 1/2 or equivalently tau less than 3. So that's sort of the mean field calculation that makes you think that when tau is less than 3, you expect slow extinction because the infection can survive, but it won't work if tau is bigger than 3. However, this mean field calculation does not take into account an important effect that's present in the static case and also in our evolving case sometimes, and that's the fact that vertices of high degree can keep the infection just with the help of their neighbors for a longer time than their recovery time. So if you assume that you have a vertex of degree k, which is of bigger order than lambda to the minus 2, if such a vertex is infected, they have a lot of neighbors, and they will infect their neighbors. So typically, if they have k neighbors, on average, before they recover, they infect k times lambda neighbors. Okay, And when they now recover, they're in a sea of, they're connected to a lot of infected ones, so it's very likely that they get reinfected instantly, right? So in fact, there are lambda times k, this is the number of infected neighbors, clocks with rate lambda that want to reinfect, and there's just one chance to get out here, and that's if you update. Because when you update, you leave the room and you're no longer exposed to all these infected people. So recovery is only sustained if this kappa clock wins against this this one clock with rate kappa wins against the lambda k clocks with rate lambda. So the probability, with probability lambda squared k over kappa plus lambda squared k, you will be immediately reinfected. And if lambda squared k is of bigger order than 1, this is very close to 1. And therefore, in this case, the infection stays alive, the recovery is not sustained, and it will do so until this unlikely event happens, that the update happens straight after the recovery, and that will be of order lambda squared k time units. So one of our, in this case, a star on its own, just with the help of its neighbors, introduces a different time scale on which it can operate. And if we want to do the mean field calculation, again taking this into account, the only thing that changes is that in order to pass the infection to a neighboring vertex, you have more time than 1. There's a hidden times 1, that's sort of the recovery time. You have more time than 1, namely lambda squared k, and k is the degree of a star, and the simple calculation shows that this is a of lambda to the minus gamma. So your new calculation, sort of topology-based calculation, replaces the time scale 1 that's not written here by lambda squared times a of lambda to the minus gamma. And when you do this, and you plug in your integrals, you will see that it now works when tau is less than 4 instead of tau less than 3. So that explains the different number occurring here. Okay, so so we've seen that there are different strategies at work, and in order to make these strategies visible, we look at a quantity called the metastable density. So that's the density of infected vertices at a sort of typical time before your infection dies out. So you look at the expected proportion of infected vertices at time t, and you look at a time which is going to infinity slower than exponentially, and then you look at the limit. So this is the expected proportion of infected vertices at a time when you expect to be in the metastable state, and that, if this limit is rho of lambda, we're interested in this, how this decays when lambda goes to 0, when you make the infection slow. And here is the result. So again, we're in this evolving network case with factor kernel. We look at the metastable density, and then you discover that this decays as lambda goes to 0 with 2 different exponents. There are 2 over 3 gamma minus 1, or gamma over 2 gamma minus 1. Maybe these numbers don't matter so much, but what you see is a difference here occurring when tau passes the value 5/2. And that corresponds to a change in the strategy which is sort of optimal for the infection to survive. And this, if you look at it, corresponds to what I've explained before. So there are the 2 strategies that you can have. Either you use this delayed mechanism where these stars hold the infection with the help of their neighbors for a longer time scale, lambda squared times the degree, a of lambda to the minus gamma. But of course, this is only of bigger order than 1 if A of lambda is small enough. So you have to have a rigid definition of stars for this to be good. So sometimes this is not worth it because the infection spreads so quickly on the network that that you can work with a bigger set of stars, and that happens when gamma is bigger than 2/3. In which case you would have the time scale 1. Okay. If you have these strategies, how do they express themselves or manifest themselves in these exponents? Well, the set of stars has a density of A of lambda by definition, and A of lambda goes to 0, so the stars themselves don't create a density of infected vertices. But the neighbors of the stars are enough, okay? And this number here is the density of infected vertices that are neighbors of stars. So there's a factor A of lambda, which is the density of stars. A of lambda to the minus gamma is their degree, so this is the intensity of neighbors of stars, and lambda is the proportion that's infected. And when you look at this, then this gives you this exponent here. And the same in this in this second mechanism. So the two mechanisms differ in one way, and that's the time scale. Okay, so there are two possible time scales, and depending on how inhomogeneous our graph is, one or the other is better. That explains this transition in this that we see in the metastable density. Okay, quickly a look at the preferential attachment kernel. So everything I've said so far was for the factor kernel. Preferential attachment kernel is completely different. So if you look at this case, remember we had a fast extinction phase showing up for the factor kernel. That's not the case for preferential attachment. You always have slow extinction here, but you still have a transition now at tau equals 8/3. Between two different exponents for the metastable densities. And again, this corresponds to two different strategies for the infection to survive, but the strategies are different. So, and they're different in the following sense. When gamma is in both cases, there are delayed strategies. So it's always worth waiting enough so that that a star can sort of keep the infection by itself for a bit longer. But then there's a difference in the mechanism how the infection spreads from one star to another star. When gamma is less than 3/5, or this is tau equals tau bigger than 8/3, then we have what we described before. So the infection passes from one star to another star directly. But when the network is very inhomogeneous, gamma bigger than 3/5, then it's worth using a connector, a bulk vertex, as an intermediate step. So in this case, if you are infected and you have an office neighbor, you're not infecting your office neighbor direct by going to his office and passing on the infection, but you're teaching very big classes, both of you, and you pass the infection to a proportion of your students, and a proportion of these students will be also in the other person's class, and via the student they will get the infection. And that's a better way if gamma is bigger than 3/5, and because there is this different strategy, we will have, this will manifest itself with a different exponent here. Okay, so again, two different strategies, but there is a difference in so the nature of this change. Okay, oh yes, very good. Right, so this is my main slide, because now it's getting interesting. So we've seen what happens when we have the mean field case. So whenever the infection wants to reuse an edge, it will have updated and you have a new situation. We have seen we know what happens in the static case, and we also know from the two theorems I've shown you before what happens when the network evolves on the same time scale as the contact process. Now we want to interpolate between these situations, and in order to do so, we'd make the update rate of the vertices depending on the degree, or more precisely on the rank or the typical or the expected degree. So vertex number I updates now with the rate kappa, that's an irrelevant constant, multiplied with n over I to the gamma, that's the typical degree of vertex I, to a power eta. And eta is a real value. So when eta is positive, we speed up the updating, and when eta is negative, we slow it down. So that we can hope that when eta passes from -infinity to +infinity, we pass from the static case to the mean field case. And there is a long theorem which gives you all the metastable exponents for these situations, and I'm not showing you the theorem, but just the phase diagrams that are behind this. Okay, so let's look at the left picture. That corresponds to the factor kernel case. On this axis here is tau, that's our power law exponent, passing from 2 at this end, at this point to infinity. And on this axis is eta, which shows how the update rate is speeding up. So when eta is -infinity at the bottom, that's the static case, and at the top, it's the mean field case. What I've shown you so far is the case eta equals 0, where we have a constant update rate, and we've seen that up to 5½ the best strategy was given by no time delay, so quick direct spreading strategy. Up to 4 there was this delayed direct spreading strategy, and beyond 4 we had fast extinction, no successful strategy for the survival of the infection. Right? So if you go up, if you update quicker, the delayed mechanisms become less attractive, less successful, which is not surprising. And when eta passes the value 1/2, they die completely. That's not a not very hard calculation that shows you that when eta is bigger than 1/2, then then the scale with which you update is too fast compared to the recovery rate for this to succeed. And from eta equals 1/2 upwards, you see the mean field behavior. So you update so fast that it's just like every time you want to use an edge, it's already updated. Okay, so this is tau equals 3. This is the transition that was observed by Pastor Sotoras and Vespignani in the mean field case here. So then, when you look at this, this moves from 3 to 4 here, when eta moves from 1/2 to 0, and then it goes with a different angle on here. So the delayed direct spreading phase keeps existing, but when you're in the static case, this delayed direct spreading phase is no longer there. You have always slow extinction, but a phase transition between the quick direct spreading and a phase of delayed spreading, where you just have to make the A of lambda sufficiently small so that you have a delayed strategy. And that's already so small that the spreading is happening without any further restriction of the A of lambda. So the case that eta is -infinity, the static case, in this case, Mountford, Wallersin, and Yao in 2013 calculated the metastable densities. They calculated them even with exact logarithmic factors, and they noticed this phase transition here between these two mechanisms. Okay, so that's the phase picture and sort of the full interpolation in the factor kernel case. In the preferential attachment case, picture looks quite different. Again, this is just a generic calculation from eta bigger than a half. Delayed strategies don't survive, and we have the same behavior as in the mean field case with a transition at tau equals 3 between a successful strategy for long survival of the infection and fast extinction. And then there is this strange shape where we have the delayed indirect spreading. So we use a different time scale and pass the infection via connectors from star to star, and the delayed direct where this infection moves from star to star. This eta equals 0 is the one where I've shown you the theorems. You don't have fast extinction, but two different delayed strategies being successful. And when you pass down to negative values of eta, this delayed phase here starts kicking in. And if eta is less than -0.5, that's what's always going to happen. Okay, so these are these phase diagrams, and as I say, what we actually prove is that for each of these phases here, there is a certain metastable exponent. And the metastable exponents, when you pass these phases, that's still continuous, but not differentiable. Oh no, this is a bad transition, because here there is no metastable exponent for the fast, but when you pass these lines here, it's continuous. Okay. Right, 5 minutes for, before I show you the proofs, a very quick picture for the edge updating. We can also prove. So now we update edges, and the rate of update we also make dependent on the expected degrees at the endpoint with an exponent eta, and then you see this much easier phase diagrams. But maybe one feature that's interesting from in the previous one here. Maybe you have noticed from the kernels, when gamma equals 1/2, the two kernels are the same, because then gamma and 1 minus gamma are the same. So sanity check, gamma equals 1/2 is tau equals 3. If you make a cut at tau equals 3, the two pictures should look the same. But they do. Okay. Okay. And this sanity check also applies in this picture here, where the relevant dynamics is much slower, because what matters are the vertices of big degree, and they can't update all at once. So this delayed spreading phase is rather large here. Again, it stops at eta equals 1/2. And indirect strategies can only succeed in the preferential attachment case. Okay, so, right, 5 minutes for the proofs. So I've described these strategies, and if you believe in these strategies, this gives you lower bounds for the metastable densities by sort of rolling up your sleeves and showing that the strategies work, right? So you show that the strategies work, and then you have a lower bound on the number of infected vertices, and that gives you sharp, if you do it, it gives you sharp lower bounds for these metastable densities. For the upper bounds, you potentially have to show that the strategies that you've dreamt up are the best ones available, which in theory is the harder task, unless there is some good mathematics that helps you. In this case, we have a strategy or a technique that helps us. We do two things that probabilists like to do. We first simplify the model by coupling it to an easier model, in this case a kind of mean field model, and then with this easier model, we use a martingale technique to give upper bounds. And this is the easiest, this technique, at the end it's pretty elaborate, but it's relatively easy if you want to show the extinction of a fast extinction phase. And that's what I want to share with you. So first of all, the coupling. So we've said that most of the recoveries are useless because most of the recoveries of the stars are useless because they immediately get reinfected. So we simplify the model by only taking sustained recoveries into account. And if we have fewer recoveries, we potentially have more infections, so that gives an upper bound, which is exactly what we want. Okay? So this is a mean field model in the sense that there is no graph for us to remember, but every vertex can have now 3 instead of 2 states. It can be healthy, ready, which is a form of infection, or infected. And the state ready means that the vertex is infected, but ready to recover. Okay? So I said that I've explained so far that the recovery is successful if it's followed immediately by an update before a reinfection happens from the neighbors. This is one of the 2 mechanisms that can make a recovery successful. The other mechanism is the other way around. You first update, and then you're immediately followed by a recovery, because then if you update and then there's a recovery, there's no time in between for you to infect the other people in the room. Okay? And both of these things are equally likely, and it's enough to look at one of them. And in this, for the lower bounds, we look at the other one, but for the upper bounds, we look at this. And why is this so good? Well, if you have first an update and then the recovery, the update destroys the information about the network. So there's a good chance that a mean field model is good, because for this strategy, you don't need the update, need to know about the networks, because it's just been updated. So there is no information present there. And that's what we use here. So recovery and update times are taken from the original process. We use for the infection times, the mean field rate, lambda times Pij, and if an edge infection time clock rings and one of the vertices is not healthy, then they both become infected. Not ready, infected. Okay, and how do you recover? Well, if you're infected and there's an update time, then you become ready. And if then there's a recovery time that hits a ready vertex, then you become healthy. Okay, so this state ready allows us to recognize if you have an update immediately followed by recovery. And that's then a sustained recovery. So this process here has no graph information, and it can be coupled to the original process in such a way that every vertex which is infected in the original model is now either ready or infected in the mean field model. And all we have to do for an upper bound is to study the mean field model, and studying mean field model is something we can do. And my favorite technique is Supermartingale argument. So you set up this kind of score process, M of t. That's sort of the predicted infectiousness of the system at time t. So you go over all the vertices that are ready, and this score S1 of this vertex is the expected degree, that's n over I to the gamma, squared. Because if you are a vertex and the number of recoveries that you see before you update is of the order of the degree, and the number of vertices that you infect is also of the order of the degree. So it's like degree squared. And if you're not ready but infected, you have one more cycle of recovery, so it's plus the typical degree there. And then you calculate the drift, so the expected increase of this score given the state of the chain, and you see that it's something negative minus some constant times the score. So if you now take z of t as log m of t plus 1 plus this drift, then the drift by the chain rule is negative, and you have a supermartingale up to the time when when you have extinction of the infection, then the score becomes 0. And if you have a positive supermartingale, you can use the optional stopping theorem, and it tells you that the expected extinction time, so at the extinction time the score is 0, so log of 1 is 0, and you just have the drift. So this is expectation of z at the extinction time is expectation of the extinction time multiplied with c times n to the gamma. Now this optional stopping tells you that this is less or equal the same constant multiplied with the state at time 0. Would be reasonable to assume that at initial time everyone is ready, but it doesn't matter too much because it's in the log, so it's log times some power of n, so up to constant. This gives a log n, and the n to the gamma is there. So that's the bound on the expected extinction time that we get from this simple method, and that was just for the constant update rates and for the fast, for showing the possibility of fast extinction, but you can refine this method to give you upper bounds on the metastable densities in all the cases that we've looked at. And yes.
Thank you very much. Other questions or comments? Then Svante.
Hey, thank you. So this was very nice results, very nice complete phase diagrams and so on. But I have a question. Much of your talk you used the intuitive description. You divided the vertices into the stars and the rest.
Yes.
So obviously this is a gross simplification. It's partly artificial since it really is a smooth distribution of degrees, as we know here. And some of the stars are really superstars with a lot more and so on. So do you have any intuitive explanation why your intuitive explanation with just stars and the others works so well, and you can ignore that the degree distribution really is more complicated?
Well, the secret lies in the questions that we ask, right? I mean, because we ask essentially only questions that are the limiting behavior as lambda goes to 0. We only want to know whether lambda critical is 0 or not. And for this, it is enough because well, I mean, it's also represented by the fact that the metastable densities are just created by the neighbors of the stars. So this is sort of just focusing on this one regime where it's relevant. If you want to know more, you have to work harder. Then you have to take the whole structure into account. So if you want to have a reasonable estimate on the critical lambda, for example, in the case where it's not 0, you would have to do this more thorough analysis. But here we've been incredibly lucky that we can get away with this relatively rough look.
So in the proof, do you also use this separation of stars and non-stars part of it? I mean, this Supermartingale showed at the end, it seems that you just treat all vertices equal with some degree-depending weights there. But in some of your lower bounds, you use this intuitive star argument you told us with some more refined version.
Yes, in the lower bound, I mean, we have to show that the strategy works. So in particular, for the large eta regimes, you have to use independence in a good way. So for example, at some point, you can sort of keep the connectors fixed and work just on the set of stars with connectors conditional on the connectors. So it's heavily used when we do this. Yeah.
Thanks for good questions. Maybe due to time constraints, we have one or two more questions or comments. Do you have any? Yeah.
So you had these two models, the kernel, the factor kernel and the preferential attachment kernel. So they have the same degree distribution, but
Indeed.
Is there some topological difference between one and another, which will explain the difference a bit intuitively, the different phase diagrams?
Yes, there is a big topological difference, so for example, when tau is less than 3, so in both these cases, you have doubly logarithmic short typical distances between randomly chosen vertices in the largest component. But if you look at the structure of these paths, in the factor kernel case, you go for most of the paths to increasingly high-ranked vertices, and in the case of the preferential, that's for the factor kernel, and in the case of preferential attachment, two very high-ranked, so low-index vertices are typically not directly connected, but they're connected via a connector. So the typical distances in the preferential attachment are twice what they would be in the factor kernel. And that's just one, and that's not so surprising, because the sort of recursive build-up of this preferential attachment networks leads to the fact that two old vertices, well, when the second old vertex was created, the older one was not that old yet. So the effect is stronger when you wait for some time and have a young one, and then when they're really both very old. So this leads to a substantial topological difference. There are also other things. If you look at the size of the giant component near criticality, this is now for the case that tau is bigger than 3. The giant components are much smaller in the preferential attachment case than in the factor kernel. There are lots of topological differences between these two models. But most of the models that lead to the factor kernel, they're all the same, more from my rough point of view.
Thank you very much. So let's continue the lively discussion during the coffee break, and thank you very much. And let's continue with the talk.